Hello everyone. This presentation is brought to you by Ala Abdel Aya Jafar, Zahra Badr, Zahra Abdel Ghaffar, Aya Zamir, and Fatma Marshad. I am Ala, and on my behalf of our team, I'll be walking you through our work, which was originally delivered on May 24th, 2026. Application of Euler's Turbomachinery equation to centrifugal pump. Let's get started with introduction. Centrifugal pumps serve as the backbone of modern industrial and agricultural facilities. Their paramount importance stems from their geometric simplicity and high operational efficiency in fluid transport and circulation. The fundamental principle of these pumps relies on converting rotational mechanical energy derived from a motor into hydraulic energy, pressure, and kinetic energy to ensure a precise and continuous fluid flow through a system. Physical and mathematical foundation. Bernoulli and Euler. Their performance of centrifugal pump is based on a core relationship between pressure, velocity, and kinetic energy, governed by two primary principles. First, Bernoulli principle, used to describe the external state of the fluid and the distribution of energy between pressure and velocity during transport in the hydraulic system. It states that pressure is inversely proportional to the square of velocity as shown in the equation. Second, Euler's pump equation. This equation is the vital link in energy integration, describing the transfer of mechanical energy from the rotating impeller vanes to the fluid itself, while Bernoulli described the fluid's path. Euler equation describes the mechanical work the pump grants the fluid as an internal energy source. Structural and dynamic components. To understand the hydraulic mechanism, the pump must be viewed as an integrated system of precision part work in total harmony. First, rotating assembly. It's including the impeller. It's the heart of the pump, responsible for accelerating fluid via centrifugal force, and the shaft that's supported by a shaft sleeve to protect from chemical and mechanical wear. Then we have stationary components. Volute casing acts as an energy converting, reducing flow velocity to increase the pressure, and a stuffing box with a mechanical seal prevent fluid leaking or air ingress. And finally, we have a mounting accessories. Ensure precise element in vibration absorption to guarantee a longer operational lifespan. And all this part is in the figure as it's shown.
Firstly, the fluid enters the impeller eye at low pressure. This is where the pumping process begins. This section happens because the pressure at the impeller eye is lower than the pressure at the inlet, so the fluid is naturally drawn into the center of impeller. Then the impeller rotates at high speed. This rotation gives the fluid a very high velocity. The velocity increases at the impeller edge. The outer part of the blades moves faster, so the fluid gains even more speed. Next, centrifugal force pushes the fluid outward. As the impeller spins, the fluid is forced away from the center. Finally, the volute converts this velocity into pressure. The volute slows the fluid down slightly, and that increase in pressure allows the pump to deliver the fluid efficiently. In short, the fluid enters at low pressure, gains speed, moves outward, and the volume turns that speed into pressure.
Euler's equation, the mathematical core. Euler's turbomachinery equation relate the impeller motion to the energy gained by the fluid based on Newton's second law for rotational motion change in angular momentum. معادلة أويلر تربط معادلة أويلر الآلات التوربينية حركة المراوح بالطاقة المكتسبة للسائل اعتمادا على قانون نيوتن الثاني الحركة الدورانية بتغيير الزخم الزاوي velocity triangle or fluid velocity. To understand the equation, we have to understand how the fluid velocity is broken down at inlet and outlet at the blade using velocity triangles. So the components are U peripheral velocity of the impeller, U the equation omega multiplication R, V absolute velocity of the fluid, U relative velocity of the fluid, VW world velocity tangential component of absolute velocity which is directly responsible for energy transfer. مثلثات السرعة أو سرعة السائل. لفهم المعادلة يجب علينا فهم كيفية دخول وخروج السائل من على المراوح باستخدام مثلثات السرعة. U the component are U peripheral velocity السرعة المحيطية للسائل، V السرعة المطلقة للسائل، W السرعة النسبية للسائل، VW سرعة الدوران وهي المسؤولة عن نقل الطاقة. The mathematical formula for theoretical head الصيغة الرياضية للنظرية الرئيسية HE equal 1 division G U₂Vᵤ₂ minus U₁Vᵤ₁. In most well-designed pumps, the entry radial VW1 equals 0. Simplifying the equation to في معظم المضخات المصممة جيدا يكون الدخول شعاعيا ما يبسط المعادلة to HE equal U₂Vᵤ₂ division G. Now the particle application numerical example. تطبيق عملي لمثال عددي. The project data بيانات المشروع impeller exit diameter قطر خروج المروحة 0.3 متر rotational speed السرعة المحيطية 15,000 RPM mean exit angle 13 degree flow velocity 3 meter on second. The assumption radial VW1 equals 0. The calculation stems خطوات الحساب المطلوب هو إيجاد الضغط. خطوات الحساب the vertical velocity السرعة المحيطية U2 equal by multiplication 0.3 multiplication 1500 division 60 equal 23.55 meter on second. Water velocity V30 23.55 equal 3 division tan 30 degree equal 18.36 meter on second. Theoretical head 20 LHE equal 23.55 multiplication 18.36 division 9.81 equal 44 meter.
How to apply Euler equation in pump design. Euler equation is the main law for energy transfer in pumps. It changes motor torque into fluid moment on Newton's second law. The equation finds the theoretical head by changing fluid velocity in the inlet and outlet. This helps to find three design: impeller size, rotational speed, and blade geometry. Finally, Euler's equation is the bridge to modern pumping system.
Rotational speed, the primary energy source. It raises the head. If lost, the pump fails to discharge fluid. Blade geometry and angles. Responsible for fluid guidance. Any defect causes vibrations and efficiency collapse. Flow rate ensures continuity and cooling. If lost, the pump suffers from overheating. Suction pressure prevents fluid vaporization. Insufficient pressure leads to cavitation and middle pitting. Fluid properties determine friction and power demand. Changes lead to motor overload. Slip factor accounts for the loss in theoretical energy. Excessive slip results in low head. Flow area defines the fluid capacity. Restrictions cause choked flow and high internal casing pressure. Mechanical efficiency relates to power transmission. Loss of efficiency causes noise, heat, and potential shaft failure.
6. Theoretical versus actual results. Euler results are accurate only for an idle pump, infinity than Van's no friction. In reality, the actual head is lowered due to 1. Slip factor. The fluid cannot perfectly follow the van angle. 2. Hydraulic losses. Friction against casing walls and eddies. 3. Mechanical and leakage losses. Bearing friction and internal fluid recirculation. Conversion to reality, where sigma is the slip factor and eta h is hydraulic efficiency. 9. Cavitation, the destructive phenomenon. Cavitation is a critical hydraulic threat. When suction pressure is too low, the fluid boils at ambient temperature. The subsequent implosion of these bubbles creates microscopic shock waves up to thousands of atmospheres, leading to mechanical pitting, vibration, and total performance collapse. To prevent this, the available MPSHA must always be greater than the required MPSHR.